Okay, so yesterday in the lab I got you to save some text in English and then asked you to go find some Japanese. Most of the machines seem to have had a tizzy fit when you tried to paste in the Japanese text. Mine worked, so I can give you my numbers here and we'll see if we can figure out some things based on those numbers. Okay? So the different formats we were allowed saving on that text editor was ANSI, Unicode, and then Unicode Big Indian. I'm presuming the original Unicode was Unicode Little Indian. You don't know what those things mean, probably. I'll think about whether they're important enough for you to know or not. And UTF-8 was the thing we had been discussing at the end of the last class. Okay? So I had the Hound of the Baskervilles, and obviously that's just all in English. And it was 320,000 bytes in ANSI. And so I believe there were 320,000 characters, and they took a byte each. No, I didn't count them. Okay? In both of the Unicode codings, it was twice that. So that leads me to believe that Unicode was using 2 bytes per character. Someone actually opened up the file in a hex editor and you could actually see that it was 00 and then the regular ASCII ANSI value. So there was half of it was just zeros. Every second byte was a 0. But had we included stranger characters in there, it would have been able to handle them in the Unicode format. In UTF-8, we notice that it's roughly the same size as the pure ANSI. I don't know why it was slightly bigger, actually. I simply don't know. But you could see how we're seeing there some of the advantages of UTF-8. And that the great benefit of UTF-8 was that it could accommodate lots of foreign characters, but if you only had English, the English document wasn't twice as big or 4 times as big. It turned out to be roughly the same size. So you got the flexibility without the cost. You could keep the files small. Now, if you did venture into strange scripts, well, you know, it can accommodate those, and obviously the size would expand. But if it's just plain vanilla English text, you get to pay for plain vanilla English text and nothing more. Here I took what I believed was Rashomon, and it was 6,000 and odd characters. When I tried to save that as plain vanilla 1 byte ANSI, it just went bananas. There was nothing preserved. It was just gibberish. When I saved it as Unicode, it was 12,000 bytes. And I think we were able to conclude there that it was using 2 bytes per character. It was longer in UTF-8. That suggests to me that maybe in the 2 bytes, there wasn't enough to code it properly. And that if I was to open it up again, I might find some places where it failed. That there was a value whose code point was so far out there that it wouldn't fit into 2 bytes, but I'm not sure. Okay? We know that, we'll look at it in a minute, this could also just be as a result, actually, I scratched what I just said. It's more likely, okay, that this extra space here is as a result of UTF-8 being a bit inefficient. In that what could have been coded in 12,000 bytes using 2 bytes per character required more space in UTF-8. Because when we go back and look at it again, you'll see we're wasting a lot of bits when we have the header and the continuation, when we have those flags to tell us what they are, we're losing a lot of bits. And that's probably what happened there. So maybe if I went back in here, I wouldn't find any issues. I had 1,000 characters in English, and that took approximately 1,000 bytes in ANSI and 1,000 bytes in UTF-8. Then I replaced 200 of the 1,000 with some Japanese characters. Again, attempting to save those using bog standard ANSI with just 1 byte per character. Just wasn't having it. The English was fine, the Japanese went bananas. In 2-byte Unicode, sure enough, it was just double the size. And what's interesting is that with UTF-8, it was closer to 1,300 bytes. Okay, so 1,000 characters, 1,000 bytes when it was in English. Although it's closer to 13, I want to say it was 1,200. What kind of inferences can we draw from that? So I had 1,000 characters in English. I replaced 200 of them with Japanese, and the size went from 1,000 to 1,200. Almost. Remember now, I didn't add 200 Japanese characters, I replaced 200 English characters with Japanese. So each Japanese character used 3 bytes. No, there may have been a few, give or take. So I think looking at these numbers, we can infer that the Japanese required 3 bytes in UTF-8, but it only required 2 bytes in plain vanilla Unicode. If your document was all in Japanese, it might be cheaper to save it in 2-byte Unicode. But here, at that price, we got our English text very cheap. We only paid 1 byte per character for the English. And then we had to pay a bit more for the Japanese when we had it. So Unicode, this would be 32, I guess, UTF-32. That's inefficient for just plain English.
16, isn't it?
Is it 16?
Double it.
You could have me there now, I'm not sure. But the Unicode uses the same amount of bits for each character. If it's all English, that's wasteful. If it's all Japanese, that's very good value. And with UTF-8, it expands it expands the number of bits it needs to do the business. Okay, so we're going to look at that again. So I think we're seeing there in those numbers, we're seeing some of the features of UTF-8 live, so to speak. We have evidence that our understanding is reasonably correct. Slideshow. So like I had been saying,